Okay, continuing with seeing my area, multi-area OSPF. Now looking at features and characteristics of multi-area OSPF. Right, the design option with multi-area OSPF can offer following advantages: smaller routing tables, reduce the link state update overhead, reduce the frequency of SPF calculations. Right, so here we have a perfect example in multi-area. We have area 1, area 0, and area 51. This is our backbone. Right. Instead of sharing my LSAs with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 routers. Tikawaisa some area 1, it means one router is sharing information with other 10 routers. Instead of having that, a segment, it means my routers are in area 1, they communicate with each other. So instead of 10, let's say I'm going to communicate on 4 border. I'm going to communicate on 4 only. Right. I'm going to communicate on 4 only instead of 10. What does that help? How is that an advantage? How is that an advantage? It means processing a router, instead of processing information from 10 routers, it will process information from only the routers arm area. Therefore, we have reduced link state updates overhead. Designing a multi-area OSPF with smaller areas minimizes processing and memory requirements. We've touched on that. Reduced frequency of SPF calculations. Right. Area 1 mukatika change. Change yoyo inodiliwa nayo area 1. Instead, area 51 receive one update chete yekuti paitika change. But that does not affect, since I come area 1, it doesn't affect this area 51. So basically, those are the advantages. You go on multi-area OSPF. Most importantly, the easiest one to get is obviously nyaya processing. Instead of processing information in my routers ASRM network, you only process information here. My routers are remove area yako chet. And basically, that's it with multi-area OSPF. OSPF v3. Right, I already mentioned the issue to do with OSPFv2, which you can directly relate with IPv4. With OSPFv3, we are now talking of IPv6. It's almost the same thing, the same processes happens. Important thing to know, and the two processes are independent. So v3 inoita zvayo, v2 ichiita zvayo as well. They are independent processes. But how it works, the process itself is the same. Kubva pa-adjacency, kushare ma-DVDs, until masvika pa-algorithm mugadzira routing table renyu. It's almost the same thing. Right. OSPF operation. Right. Here we are going to describe, it's almost sort of repetitive because we've been touching on almost everything that describe how does operate the process of OSPF happen. Here we look at the states. Takushandisa states to describe the process itself. Right, starting with the down state, we have the down state, initiation, init state, two-way state. What are these? Let's say I have two routers, R1 and R2. Right, in the down state, no hello packets are being shared between these two. There is no hello packets being shared between these two. That is the down state. Now, the moment a hello packet is sent, we now move from the down state to the init state. So with the init state, hello packets are received from the neighbor. They contain the router ID. Ndo send information, hello, how are you? Right? From there, hello packet rasendwa. Rauya ku R2, we are in the initiation state. If R2 responds, ne hello packet rake, hello, how are you? Inini ndinonzi router ID number yakati. Then we have transitioned from the init state to the two-way state. In this state, communication between the two routers is bidirectional. Now we have reached adjacency. Communication here bidirectional. We can send or receive my packets between these two routers. On multi-access links, the router elects a DR and a BDR, and after that, we transition into the extract state. So at this stage, but exchange information between two routers. Inini route ID yangu ndeyipi? Iyo route ID yako ndeyipi? Route ID hombe pa2 wedu ndeyipi? Therefore, ane route ID hombe pa2 wedu ndiye achaita DR in a multi-access network. Tinenge tiri pa two-way state. We'll get to describe multi-access network later, but from these three steps, we have transitioned from the down state, where we have no information at all being sent, to the init state, where one router sends a hello packet to the other, to the neighbor. Then when that neighbor responds, we go to the two-way state. We now have bidirectional communication between these two routers. All right. From there, we move to the extract state. On point-to-point networks, the two routers decide which router will initiate the DBD packet exchange and decide upon the DBD packet sequence number. So after a two-way state, we have got extract state. Pano exchange information yekuti DBD, pano exchange information yekuti marouters ID edu ndeapi, and let me see, on point-to-point networks, the two routers decide which router will initiate the DBD packet. Right. Two things. Point-to-point network, multi-access. Let's start there. I think it makes easier explanation as we move forward. Let's start with right. Let's start with understanding with point-to-point network. So we have point-to-point network, we have multi-access network. These are two different networks, right? I just thought it's easier to explain this first, because it's point-to-point, not understanding with chi. Right, with point-to-point networks, basically what we have is exchange of information between two endpoints, and it's only dedicated to only those two endpoints. So in this case, R1 and R2, this is a point-to-point network, because information over an R2, irusika over an R1, irusika over an R2, and information over an R2, irusika over an R1. Point-to-point. When we talk of a multi-access, device ready do not allow it a multi-access, it's a switch where we have a shared medium. Right, let's now say we have R3, R2, R1. This is not a point-to-point network. Why? Because R1 can communicate via the switch with R2 and R3. A broadcast can be sent R2 and R3. So therefore, flow of information is now not dedicated to only one end device. One device, let me just say. It's dedicated to probably every other device in that network can broadcast. So the way the OSPF process works in these two is different. Because in this case with the point-to-point, number one, we don't have reason to elect not DR, backup designated router. We don't have reason to do that, because information exchange between only two routers. With this one, we have to find with DR ichi, BDR ichi, so that the designated router do take over the functionality. It's sort of the central, it becomes the central router. Routing do secret information, then it is then propagated to all other routers in the network. So two different things between point-to-point and multi-access. Right now, with multi-access, pangatiri pa two-way setup. That ndo paru determine DR and PTR. With point-to-point, per X start state, ndo paru determine kuti achatanga kushare DBD ndiani. So they actually discuss, panosenda hello packets, information irimo ndiyo inoshandiswa kuti mukuru ndiani panapa. Saka ndiani achatanga kusenda DBD packet. DBD packet rikasendwa, let's say R1 has been chosen kuti ndiye achatanga kusenda DBD packet. anosenda dbd packet rake roreceive then R2 responds with the dbd packet rake as well. So basically this is the extart state where there is an exchange of my dbds, where there is the starting of exchange my dbds, the process yekuziva kuti ari kufanira kutanga kuexchange dbd ndiani, right? Then taziva kuti ari kutanga ndiani, we move to the exchange state. The exchange state, this is where routers exchange dbd packets. If additional router information is required, then transition to loading, otherwise transition to full state, right? Taziva kuti ari kutanga kusenda dbd ndiani, we move to the exchanging yema dbds edu. Tikapedza kuexchange ma dbds edu, if there is no any other additional information required, it means tinobva pa exchange state kuenda pa full state, with the full state being the link state database of the router is fully synchronized, right? So pa full state apa synchronization is complete. But if we have missing information, I've talked of LSR's requests and updates. If there is missing information, then from exchange, we don't move directly to full, to end up loading. Where by loading, my requests are sent, there is missing information, per information, then an update is sent. Can update send, then we finally move to the full state, where the database of the router is fully synchronized. At this stage, LSDB redu topology table yedu apa tinenge tanayo at the full state. Right, so basically, this is the operational state of a router edu. Summarizing, down state, no communication between the two. Panotanga is yellow packet, we move to the init state. Yellow packet rasika from neighbor. If the neighbor responds, takwenda pa two-way state. Pa two-way state, ta exchange information, initial information. Takutoziva kuti wacha elect as DR and BDR ndiani. From the two-way state, we go to exchange state. Exchange state inotanga ne X start state. Ndoba inotangira. For X start state, we decide between two routers, who sends the DBD first. Tika decide out who sends the DBD first. Takutenda pa exchange state yedu, we exchange ma DBDs edu. Kana tapedza ku exchange ma DBDs edu, takuenda pa full state. If we have missing information, we don't transition directly to full state, tuenda pa loading, where a request is sent with missing information and an update is sent back to what is the missing information. Then from there, we go to the full state. Right. Moving to, establish neighbor adjacencies. To determine if there is an OSPF neighbor on the link, the router sends a hello packet that contains the router ID. The hello packet is sent to the reserved or OSPF router's IPv4 multicast address. Right. Keep in mind this address, 224. These are typical questions that you'll be asked. There's also another one in A6, I think, designated routers. Because the address you ichi. So this is the address in a Shanskane Nema routers to share routing information. It's a multicast address. If you are sending a protocol, if you're sending protocol information to all the routers in the network, you use this multicast address. If you're sending information to the designated routers, my DRs, information you send to my DRs, you use 224006. Take note of my addresses, very important. All right. So establish neighbor adjacency, we've discussed this already. To send my yellow packets, then we establish adjacency. Right. The OSPF router ID is used. Is it the same in IPv6? Voila, it's the same. It's a multicast. I think it's FE. No, it's not FE. Let me see. My FE in the link local. Right, but it's the same. A multicast address. Responding to Ryan. Is it the same in IPv6 in a chance for :2? Yes, it's the same. It's a multicast address. So in IPv4, we use this. In IPv6, we use address in :2. I'm not sure about the specifics because I got one day my TV my multicast. All right. A router ID is a 32-bit formatted like an IPv4 address as assigned to uniquely identify a router among its peers. When a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. Right. I want to talk about the router ID here. Very important. Router ID. Router ID key. So in an OSPF network, a router ID is used to identify the router. In an IP network, an IP address is used to identify a device in that network. In an OSPF network, what identifies a router is the router ID. Router ID key, it can be it's a 32-bit number, the same with IP, which one concept manually configured. Number one, it can be manually configured. If not manually configured, then the highest address, loopback interface becomes the, let me check. The highest address, loopback interface becomes the router ID. If not, then the highest IP address, number 17. If not, the highest IP address, interface becomes the, all right, let's start with the loopback interface, which is the highest. Right, number 3, we look at the interface ID, highest as well, right? Right, so I'm saying the router ID, it identifies a router in the network. Number actually, one, it can be manually configured. When you manually configure, it means sort of you're manipulating a choice yekuziva kuti achaita DB, achaita designated router, I mean, neachaita backup designated router ichi. So anenge ane highest ndio anoita designated router. So raunoti rite highest router ID, unoriconfigure ne highest router ID, then it becomes the designated router. Or you are sort of manipulating process yekuchuza yepa extract. Yekuchuza kuti ari kutanga send information ndiani. We consider the router ID. So you manipulate nekuisa manual configuration there. If not manually configured, we have the highest address ye loopback interface per router rako. Kana usina loopback interface configured, then we look at my interface IDs. The highest interface ID per router yako becomes the router ID of a router rako. So this is very important in 3 issues. How is the router ID chosen per router? Manual configuration, highest loopback interface. If not, then the highest interface ID. We see my importance in router ID as we move. Right. The process routers used to establish adjacency on a multi-access network. Down to initiation state, when OSPF is enabled on the interface, R1 transitions from down to init and starts sending OSPF hellos out of the interface in an attempt to discover neighbors. We discussed that. In the init state, a router receives a hello packet. Then the two-way state, it responds to that hello, right? When R2 receives a hello from the previously unknown R1, it adds R1's router ID to the neighbor list and responds with a hello packet containing its own router ID. By hello, per initiation state, nepa two-way taku exchange information iri exchange iri very important papo is the router ID. R1 receives R2's hello and notice that the message contains R1 router ID in the list of R2's neighbors. R1 adds R2 to the neighbor list, transitions to two-way state. If R1 and R2 are connected with the point-to-point, they start X start. If R2 are connected on a multi-access network, elections for DR and BDR start. Right, election for DR and BDR. The DR and designated router and backup designated router election occurs when router with the highest router ID or highest priority is elected as the designated router, and the second highest is designated as the backup designated router. Right. So this is just a summary of all the things that we've been discussing here, with the highlight of the difference between a point-to-point network and a multi-access network. Kana tine point-to-point, tabva from the down state, hapana chatiri kuziva. Initiation state, hello packet rovha rasendwa. Two-way state, bidirectional exchange. Hello packet ravha receive ravha radzoswa back indo responda. Basically tam two-way state. In the two-way state, tazivana kuti router IDs edu ndeapi. Kana tiri pa point to point, that information ndo ichauzwa kuziva kuti achatanga kusenda information ndiani, which is the X start. Achatanga kusenda database description ndiani, which is the exchange start state. If tisiri mu point to point, tiri mu multi access, information ema router ID ndo ichatanga kuuzwa kuita DB or BDR election. Then election yacho inoshandise it use the highest router ID and the highest priority. Kana pasina manually configured router ID, it uses the highest loopback interface. Kana pasina, it uses the highest IP, the highest interface ID address, basically. Right. Synchronizing. After the two-way state routers, I think this is mostly a repetition of all the information at data, but I describe my states. So with the two-way state routers transition to database synchronization state, decide the first router. The router with the highest router ID sends its DBD first. That's a point-to-point network, triple X starter. Tavam two-way state, tawenda mu X start state. Exchange of DBDs, as many as needed to convey the database. The other router must acknowledge each DBD with an LS acknowledgement packet. So for every DBD sent, the neighboring router inofana respond to DBD rasvika, and that is the acknowledgement. DBD rasvika, okay, then ndosenda warangu uyo acknowledge kuti DBD information yasvika, and basically that's it. Send an LSR. Each router compares the DBD information with the local LSDB. If the DBD has more current link information, the router transitions to loading state. Right? So kanampane the difference between the DBD rasendwa ne database redu ne links to database redu ndo patinopinda loading state. Why? Ndo panosenda request kuti database rangu randinaro neinformation yaonosendera zvakasiyana. What is happening? Chii chakasiyana? Ndo panosenda request, then advertisement LSA or LSU rovha rasendwa back update kuti zvakasiyana ndeizvi. We have a new link riri pakati. Loading state yapera. After loading state yapera, takuenda pa full state. After all LSRs have been exchanged and satisfied, the routers are considered synchronized and in full state. Updates are sent, LSUs are sent when a change is perceived or every 30 minutes. So we can see my updates, they are being sent. Networking angozori pane paitika change. Zviroti update rafana usendo. And update rinosendwa. Why? Because pamune mchisenda ma-DBDs, router rino compare database rayo ne-description yarasenderwa. Ikangona zvakasiyana, yakutoziva kuti something has happened. Yakutosenda request, then an update is sent. So when a change is perceived, LSR and LSU information is exchanged. Every 30 minutes, an update is sent as well. Update yo ikasendwa kana database ne-description zvakafanana, then nothing happens. We are fully synchronized. Right, the need for a DR. Now, the reason why we need a designated router, this explains why. So this is a multi-access network at mentioned. With point-to-point, there is only communication between two devices, router 1 and router 2. Panosendwa ma hello packets, tikuzoti hello packet rinosendwa kuna R2 because ndo iri directly connected to R1. Panosendwa advertisement LSA, tikuzoti rikusendwa kuna R2. Kana rikuita sort of riri multicast, then R2 anozosendawo kune mamwe arikuenda. But this is a point-to-point network between two devices. With multi-access now, you can see tane shared medium yedu panapa switch. Panosendwa LSA. rikasvika panapa rinosvika riri sebroadcast rinoti richauya panapa richauya panapa richauya panapa richauya panapa, which is no longer a point-to-point network. Now, the problems that come with that, we have creation of multiple adjacencies. Right? Zikureva kuti in point-to-point adjacency ndinoicreata between R1 and R2 chete. Ava ndovanomhoresana ndebbo here. Okay, inini ndinonzi ani route ID yangu ndiani. These two ndovana share that information paadjacency. But with multi-access adjacency now inofanira R1 iyi ichaita adjacency neiri, ichaita neiri, ichaita neiri, ichaita neiri as well. The problem with that processing yedu patinoita maadjacencies akawanda pachisendwa mabroadcast akawanda, marouters edu processing power yese inoenda kudhila nema LSA nema-hello packets, which is very unnecessary. So the creation of multiple adjacencies, Ethernet networks could potentially interconnect many OSPF routers over a common link. Creating adjacency with every router would lead to an excessive number of LSAs exchanged between the routers on the same network. An excessive number of adjacencies and LSAs being exchanged. Zviroti information yese inofanira kuprocesswa painosvika parouter inofanira kuprocesswa. If imba iri kupfuura nepaswitch up inofanira kuprocesswa. Network inoita slow because une zvakawanda zviri kufanira kuprocesswa. Right, extensive flooding of LSAs. Link state routers flood the LSAs anytime OSPF is initialized or when there is a change in the topology. This flooding can become excessive. Right, nyaya iri papa ndima multiple adjacencies ne-flooding. Kana ya excessive, what happens? Processing power is affected, network edu inoenda slow. So that's why we have the need for a designated router. Right, so designated router basically, instead yekuti every router in the network inosenda mabroadcast, kana tine DR which is chosen nekutarisa router ID or the priority, router priority. Let's say iri ndo ranzi designated router, pasenzwa ma-hello packets, apedza kusendwa paitika election process, iro ranzi EDR, iri ranzi backup designated router. Right, and now panoitwa exchange yema-LSAs. Instead yekuti this router, let's start looking at this one, kuti risend a broadcast, harisend a broadcast, rinongosenda information to the designated router. Ndo rinoshandisa, I think is 224.0.0.6 address. Rinongosenda information to the designated router. Then designated router rasenderwa information naush, rasenderwa information naush, rasenderwa information nerouter iri, rane information nemarouters ese. Instead yekuti this one could have sent a broadcast, so router ikwanisa kusendera all the devices. Instead of broadcast, every router in the network rinosenda information to the designated router. So tato reduce the amount of information that we send. Designated router ndo rinozodistribute information ma-updates ese to every other device. So designated router ndo rakuziva kuti ndikuudza iri kuti chii, ndikuudza iri kuti chii, ndikuudza iri kuti chii, ndikuudza iri kuti chii. So we've reduced the number yema-broadcast ari kuitwa because instead of ma-routers ese emunetwork kuti asende broadcast, haachasende broadcast, akusendera information to the DR and the BDR. Inosendwa kwese. The reason why we have a BDR is so that pano, let's say router iradakwa. Hey, router iradakwa, what happens? The BDR takes off. So basically, this is the need for a DR in a multi-access network. Right, an increase in the number of multi-access network also increases the number of LSAs. The flooding significantly impacts the operation. We touched on that. On multi-access networks, OSPF elects a DR to be the collection and the distribution point. Right. So instead of having collection and distribution by every other device router, only the DR ndio inenge yakuita zvese izvozvo. Zvinoti munosenda ma-messages enyu ku-DR, DR yo distribute, yo the distribution point. Instead yekuti every router in the network inenge rofanira ku-distribute that information. Right. So once we've selected DR ne BDR, every other router isiri DR ne BDR becomes a DR other designated router. Right. We have 10 minutes. Look better. Okay. And basically, that summarizes the concepts of OSPF. The concepts of OSPF. Right, let me try to summarize. So we've talked, I have 10 minutes, we've talked about link state and distance vector protocols. Very important. In summary, this you should know. But what is a distance vector protocol? How does it work? And what is a link state? What is the difference? Typical exam question. Distance vector versus the link state. One, distance vector, it exchanges with the neighbor, directly connected neighbor only. With the link state, it exchanges with every router in the network. Link state, because it's exchanging with every router in the network, convergence is much faster. Pakatika change. Hatina kuti ndotaura naningi, ningi wozotaura naningi. No, totaura namunhu wese, information yesendwa munhu wese, murauta rese, I mean, then tozoti pane change yaitika, we reconfigure to choose among routes, convergence in less time. Right? We discussed the issue, my type of my packets are very important. The yellow, the DPD, LSR, LSA, multiple LSAs making up an LSU, then we have an LS acknowledgement. You need to know kuti each anoshande relate to every packet per process yema states from down state to full state. You should understand kuti yellow packet rusendwa at what state. You see kuti yellow packet patinopinda pa init state ndo parusendwa yellow packets, then toenda pa two-way information exchange wa toenda pa exstart, patinoita pa exchange dbd rovha raita takeover ndo pakushayiwa dbd apa exchange, then kana tiri pa loading ndo pari kuexchange wa 2i, the request and the updates. Acknowledgement, pese pari kusendwa dbd rinofana ku acknowledgewa kuti rasendwa. So you should know kuti mapackets, where are they specifically being sent. Yellow packet kana takuloading ukaorioni unoona kwekutanga tanga. That's very important. Right? Types of OSPF packets, we've described this, the structure of the yellow packet, the link state updates, components. Right here, it's very important to know my database in their respective tables. Adjacency database, chi, you know, show my neighbors being shown in the neighbor table. Adjacency table with respect to my states area from down to full, iri papi. Panopera adjacency, my yellow packets are sendwa. I'm sure for exstart, just before exstart, ndo panenge perform adjacency database ready ba. Then after exchange, ndo panoform your link state database. Exchange rapera, then forwarding database takes over, ndo munoiswa maroutes ese anenge achuzwa after the SPF algorithm, right abasa. So you need to know my databases are. You definitely see a question in my database. But the database, the topology table, no run database rip. Tunoruana link state database. Right. Link state operation, establishing adjacency, exchanging LSAs, building the LSDB, executing the SPF algorithm, choosing the best route. We touched on this operation. Understand the difference between the single area and multi-area OSPF. The whole idea between single area and multi-area OSPF is the same idea between segmenting a very large network into different subnets. The same reasoning. It's much easier to work with smaller networks, deal with smaller networks. The network you get a breakdown in a smaller network, it doesn't affect the network. It's the same logic here. Processing, in terms of processing, router no processor information in area instead of processing information in 100 routers SRM network. So that's very important, understanding the difference between single area and multi-area. Isusu, in this course, we will touch on single area configuration only. Right. OSPFv3, that is OSPF4 IPv6. Operational states, we touched on this. Downstate, no communication at all. Patinotanga send a hello packet, term initiation state, init state. Hello packet parino respond wa tamu two-way state, bidirectional communication. After that, takuda ku exchange information. Tinotanga na exstart state, kuchoose out anotanga send a DPD ndiani. After that, we exchange our information in the exchange state, our DBDs in the exchange state. From there, we compare the DBDs, the DBD with the LSDB, the database redu, compare description in database. Kana zisiri kumecha zisiri kufanana, tosenda request, kubvunza kuti zvizvi kuitika. update rouya kuti izvi ndo zviri kuitika kusvika the description rinafanana nedatabase. Description rikafanana nedatabase, then we fully synchronized our database, and that is the full state. Right from there, establishing adjacencies, we touched on this. Synchronizing, we touched on this. The need for a DR. Understand with election a DR, it can say, we look at the router ID and the priority. Router ID, you can manually configure that, or you can use my interfaces are up my IP address. So interface panap, let's say we have another interface panap to configure say loopback. This one will be chosen first over interface normal my gig ethernet. So the loopback will be chosen first. Why? Why? Because the loopback interface is a visual interface. Very important this. A loopback interface is a visual interface. Router is always up. I don't know if down. Unless when don't read that down, you. It's just a visual interface. Unlike interface iri, rinongoita down iri. Rikaita down zvirova kuti router ID yakutochinja. Zvirova kuti network yakutofanira reconfigure itself. That's why we prioritize the loopback interface over the interface of interface ID of a router, because the loopback interface is always up. Zvirova kuti we don't have unnecessary changes in the network because link writer down. Link ukachoose this to be your router ID, link iri rikadhakwa. Zvirova kuti election process yese BDR nechi zvakutofanira kuchinja. Network yakutofanira kuita reconfigure itself, takudzoka futi process from around I think extart or init kuti tisvike futi kusynchronization. So we choose manual configuration router ID, or we use the loopback because it's a virtual interface which is always up. If all are not configured, then this one will be chosen because it tends in an alternative with the right. The need for DR flooding with the DR done. Right. I think this is it for OSPF. The next session that we'll be doing more of my configurations, which is the second chapter. Data my configurations OSPF2. I think this helps because I'll be getting a number of requests which got to an OSPF, and I hope it has been simplified as much as I can. Thank you very much for your attention. We're done.